Log on, tune in, find out. Another good idea from Cambridge.
And I'm very pleased to present Gavin Gibson from Heriot-Watt University.
Okay, first of all, thanks very much to Andrew and Darius for the invitation to come here to what was a very interesting meeting, and something for me which is a little bit different because most of the meetings I go to are in the area of epidemiological modelling. I realised when I looked at the title that I've given you a very kind of generic title here about Bayesian experimental design for stochastic dynamical models. But what I'm really going to describe is quite a sort of specific case study of the Bayesian approach applied to designing experiments for a particular kind of epidemiological model. So it's perhaps an example of Bayesian experimental design for stochastic dynamical models. It's joint work with Alex Cook, who used to be here at Cambridge and also at Heriot-Watt and is now at Singapore at the National University, and also a colleague, Louise Carrasco at Singapore, who's now involved in this, and also with Chris Gilligan from the Department of Plant Sciences here at Cambridge. A very quick overview of what I'll talk about. As I say, most of the work that I'm involved in is in epidemiological modelling, so I will give an overview of the kind of stochastic models that we look at when we analyse epidemics. I'll then focus on a particular example of epidemics, which is epidemics of populations of plants, which are carried out in artificial microcosm experiments here at Cambridge, and then describe the design problem which we want to tackle, which is essentially the problem of trying to identify the most efficient way of sampling the system in time. Now, for various reasons, which I hope I'll manage to get across, the Bayesian approach to model fitting for epidemic models does seem to be particularly appropriate, mainly due to the fact that when we look at epidemics, we only get very partial observations on the system. There's a lot of missing information, and the Bayesian approach gives a very flexible framework for doing that. And that's one of the reasons then for sticking within the Bayesian approach when it comes to trying to design the experiments. However, in order to make this feasible, computationally feasible, we then have to use quite a lot of approximation in the way that we calculate likelihoods and calculate posterior densities. So I'll try and describe some of that and then show some of the results from implementation, hopefully getting back to the kind of practical advice that we can give to people who are carrying out these experiments. So what does a typical kind of epidemic model look like? A very common family of epidemic models would be what we call the SEIR models. Here I'm talking about finite populations of fixed size. We can also do this kind of modeling for populations where the size is not necessarily fixed. But imagine we have a set of n individuals, and this population can be partitioned into four classes: a class of susceptible individuals, a class of individuals who are exposed to disease, so therefore incubating it but not yet infectious, and then after some time they become infectious and start infecting other individuals, and then ultimately they go into the removed class. Now there are a whole lot of variations of this model structure, but everything that I'll talk about will actually fall into this general class. In fact, it will be even more specific than that. Now, to specify a stochastic model for that, what we normally do is to make the common consideration that the way in which individuals become exposed is essentially a process that operates rather like an inhomogeneous Poisson process. So in other words, if we've got an individual J who's in state S at time t, then slight abuse of notation here, but the probability to become exposed in this infinitesimal interval essentially is proportional to the number of infectious individuals in the population multiplied by some contact rate beta. Now we can also formulate these kind of models spatially as well, so rather than just, if you like, sum up the number of individuals who are infected, we may actually weight their infectious challenge according to where they're located in the population. And a lot of the modelling that people like I know Matt, who's here today, are looking at spatially explicit models. But in this talk, I'm not going to look at spatially explicit models. I'll just be looking at what we call the homogeneously mixing situation. So we have a stochastic process that governs the exposure of individuals. To complete the model then, we would have to be specifying some kind of probability distribution for the length of time that an individual remains in the exposed class before they become infected. Commonly that might be modelled as a gamma distribution or a viable distribution. Similarly, we would want to have a distribution for the length of time an individual remains infectious, so therefore the time it takes for them to go from I to R. And again, gamma distributions are often used for those. So for this model here, we would typically then have a parameter vector which would have a contact rate, and then parameters which describe the sojourn times in the E and the I class. Now, one of the reasons that it's easy to formulate these models, but often very difficult to fit them, is that when you come to look at a real epidemic, let's say in a homogeneously mixing population, you only get very partial information on what's happened in the course of that epidemic. If we imagine here's individual I, and this is the time course of their history during the epidemic, there will be a point at which they may become exposed, then they move to I and then to R. The information that one might have might only be the results of diagnostic tests applied to that individual, perhaps very infrequently. There may be certain states which cannot be distinguished, so one may have a diagnostic test which can only tell if an individual is infectious, but doesn't tell you if they've actually been exposed. Typically tests will have some sensitivity and specificity, so we'll have false negative and positive results. With some of the systems that I've worked with, for example, modelling Clostridium difficile in hospital wards, you often get individuals who are never actually tested during the course of their stay. So one may never actually know whether they were exposed or not. So typically then you're working with only a very partial representation of the set of all events which have occurred during the course of the epidemic. And that really motivates the use of the Bayesian approach, which I would say over the last 15 years or so has really proved very valuable in enabling these kind of models to be fitted to data. So I know that most people here will be statisticians, but just for a very quick summary of what the main idea is here. Let's suppose we have data Y, then the likelihood principle says that, okay, all the evidence we're going to get about our unknown parameter vector in the model will be contained in the likelihood, L of theta given Y. The way in which the Bayesian approach, if you like, takes us through to some kind of decision-making framework is to say, well, what we'll do is we'll represent our prior beliefs about theta as some probability density pi of theta, and then we'll update this prior belief in the light of the observations Y using Bayes' theorem to get a posterior density for theta given Y, just proportional to the product of the prior and the likelihood. And then, as in the case that we'll be working in, theta will be a multivariate parameter. Then if we have a particular parameter that we're interested in, we're able to extract our beliefs about that parameter from the marginal posterior density of the individual components. So of course, with the Bayesian framework, the main contentious issue is how one goes about selecting a prior. And in the case of epidemic models, that is something that one has to be very careful with, actually, which, sorry, apologies. So I will say something at that later in the talk. Now, why is this particularly useful, this framework for epidemic models? Well, if I let Y represent the actual observations I have, that's only going to be a very partial representation of what's happened. So now let Z represent, if you like, the complete data, which in an ideal world I would be able to observe. So that would correspond to the time and the nature of all events that occurred during the course of the epidemic. Then the problem is that P of Z given theta, which would be the likelihood I would compute if I actually observed Z, is going to be tractable. I can write down an analytic expression for that. It's maybe quite messy, but I can do it. But if I only have data Y, then the likelihood that I would really like to work with is a very nasty looking integral over the space of all Z, which are consistent with Y. So trying to work directly with this likelihood given Y is going to be difficult because there's a very nasty integral that one would have to solve. The Bayesian framework gives a very natural way of effectively investigating that integral, because what we can do is we can consider, if you like, the hidden aspects of the epidemic. So in other words, all the events which we haven't observed, which typically, for example, will be the exact infection times, all the times at which individuals have gone from E to I and so forth. We can consider those as additional unknown parameters, And then what we do is we investigate the joint posterior density of the model parameters and the unknown data components given the observations. This joint posterior density I can write down just as pi of theta and then pi of xy given theta. This, of course, is just the probability of z given theta, or the density of z given theta. That's tractable, so at least I've got a posterior density here which I can write down up to some unknown constant. Now, if I'm able to do that, I can exploit Markov chain methods in order to come up with algorithms for investigating those densities using standard recipes such as Metropolis, Hastings, Gibbs sampling, reversible jump methods. I won't talk about these in detail in the course of this talk, but just stress that this is the general kind of techniques that one uses to fit these methods. Okay, so what's involved in Markov chain Monte Carlo? Well, essentially, you have to construct a Markov chain which has this as its stationary distribution. The practicalities of constructing these Markov chains requires you to specify ways of proposing changes to the current state, theta I xi, to obtain the next state, theta I plus 1 xi plus 1. We can often update the model parameters using Gibbs steps, but when it comes to updating the unknown or the missing information, x, which would correspond to all the unobserved infection times, for example, then we have to use usually Metropolis, Hastings, and the reversible jump versions of Metropolis, Hastings in order to propose changes to time. So a brief comment on reversible jump. It really is an extension of Metropolis, Hastings to situations where, if you like, the space of x has components of differing dimensions. So it's a way of constructing moves to jump between spaces of differing dimension. The reason that that's important for epidemics is if one has a situation where one can only observe removals from the population, then it means at the end of your observation time you may still have some unobserved infections. Okay? Now, you don't know how many unobserved infections there actually are, so that's why the space for x has components of differing dimension depending on how many unobserved infections there are. A few kind of recent examples of this approach in the literature where it's actually used in anger to fit models in a paper with Tony Pettit and Marie Forrester from QUT. We looked at fitting SEIR models to the dynamics of MRSA in hospital wards. Closer to home, Neil Ferguson's group at Imperial and also Gareth Roberts at Warwick have used these very same approaches to analyse the 2001 foot and mouth disease epidemic. So one can apply this to very large systems with a fair degree of success, although it is computationally very intensive. I'm going to look at a much smaller system now because this is the one where we're going to discuss the design problem. And this is an example of microcosm experiments as conducted at Plant Sciences. Just to say a little bit about what these experiments are doing. This is on a system which is Rhizoctonia in radish. Rhizoctonia solanae is a fungal disease of radish that affects the roots, effectively causes the plants to shrivel and die quite quickly after they're infected, and it's economically significant, and therefore there's a lot of interest in knowing how to actually control it. Now, in this experiment, there's 5 replicates each for 2 different treatments. The population sizes are 50, and what they did was to start off epidemics by inoculating the soil with Rhizoctonia and then plot over the time course of the epidemic the number of infected individuals that there were in this population. Now, there's 2 treatments. As I say, in one of the treatments, there's essentially nothing done apart from the initial inoculation by Rhizoctonia. In the second treatment, there's the addition to the system of another fungus, Trichoderma, which was believed in some way to interfere with the epidemic process and potentially could be a biological control. Now, when we look at the results from this experiment, we see that, okay, when there's no Trichoderma, generally we seem to get an epidemic that's taking off. When there is Trichoderma added, there appears to be, at least in the case of some replicates, some control of the epidemic. And the natural question to ask then is, how does trichoderma actually affect the system? What aspects of the transmission process is it actually acting on? Okay, so to investigate that, and this is mainly the model I'll be looking at for the rest of the talk, we can look at a pretty simple model for this process. I say, generally speaking, with these kind of systems, I think it's probably a good idea to start with the simplest possible model that captures the biological processes that are believed to affect what you're observing, and see how far you can get with that. And the simplest model that we have here really is one in where we have, if you like, an exposure probability for any susceptible individual, which looks like the following. If we have a susceptible individual at time t, the probability that they're going to get infected in the next little time interval essentially looks like this expression on the right here. You'll see I've got three parameters, B1, B2, and R, and B1 represents a primary infection. So in other words, this is the challenge presented by the initial inoculum of the Rhizoctonia, and that's presented to every individual in the population to the same extent. But once individuals start to get infected, then infected individuals will present an additional challenge to susceptible individuals, and that's quantified by the term B2. So I refer to these as primary and secondary infections, respectively. Now, there's a third term coming in here, which is essentially an exponential decay in that rate, which corresponds to the biological belief that as the plants are developing and the cell walls are thickening and they're becoming more robust, it becomes harder for the fungus to actually invade the roots. So think of that as a temporal decay in susceptibility. So we can formulate a model for that. Why do we need to use the Bayesian methods? What's the missing information here? This is something which I should have said. Well, each dot here represents a recorded observation, but you can see that there's periods where the system is not examined, and in some of these periods there's been a large number of infections have taken place. So in other words, we're observing the number of infections at particular times, but we're not observing the particular times of the infections that occur between them. Okay, so that's essentially why this naturally fits into the framework that I've described. Okay, so we can take this model and we can, as I say, I've used vague uniform priors here. Now, I did mention earlier that the choice of priors for models of this kind is really something that has to be thought about very, very carefully, because in fact this is a system whereby if you took if you like the usual or one of the frequent choices of non-informative priors for a rate parameter, which would be, for example, a parameter proportional to, a prior proportional to 1 over B2, let's say in the case of secondary infection. If one actually did that, one can easily show that you would have an improper posterior distribution, because you would be able to explain the epidemic with B2 becoming arbitrarily small. In other words, the likelihood does not tend to 0 as the parameter value B2 tends to 0. So one would end up with an improper prior. So I don't want to give the impression that this is just a glib choice of prior. One does need to be quite careful about how one does this, and also give due consideration of things like sensitivity of conclusions to priors. But here we're using vague uniform priors over finite windows, and we can carry out a Bayesian analysis and obtain posterior distributions for the parameters for these two treatments, and see if this gives us any indication as to what could be happening in this experiment. When we do this, we see that for the trichoderma and the no trichoderma treatments, when we look at the secondary infection process, there does not seem to be any real evidence of a difference in that parameter, in that the posterior distributions look very consistent with each other. For the quenching parameter, again, there doesn't seem to be a huge difference between the posteriors that we get. In this model, there is also a latent period, but when we look at the primary infection parameter, then there does seem to be a big difference between these two posterior distributions. So remember, these are the marginal distributions, and on the basis of that, we would say there appears to be some evidence, at least, that potentially the trichoderma could be operating by affecting the primary infection process rather than the secondary infection process. Now, conclusions like that are actually quite important biologically, because if one was thinking about how one could use this in a field situation, If it does not affect secondary infection, then there would be very little point in deploying the control after a stage when the epidemic had become established. So these kind of conclusions are practically quite useful. Now, one of the things about this epidemic, or this experiment rather, is that the sampling is extremely intensive. A huge amount of work has gone into collecting this data. I think this was actually Doug Bailey who did this experiment back in the late 90s in Cambridge, so or at least collected the data. Each one of these observations does require somebody to score all the plants in the experiment. So you can see that there's a total of 14 days have been on which the system's been scored for each of these treatments. So there's an awful lot of work goes into that, and that's a very costly resource. And the natural question to ask then is, okay, if you're going to design future experiments to study this system, can we come up with a way of identifying a more efficient way of doing it in terms of using a smaller number of sampling times? So, given that we were working in the Bayesian framework, it did seem quite natural, perhaps, to look at the Bayesian framework for experimental design to see what that could tell us in this case. So therefore, we're going to work within the framework really formulated by Muller and co-workers for identifying optimal designs, which is really I think it's a typical sort of Bayesian approach to take, where you manage to represent every problem as the investigation of a posterior density in some ways. So how does he do it? Well, we start off with our current belief regarding the parameter theta, so we have our prior. And then I'm going to think of z dashed, if you like, as being the complete future realization of the process that I'm going to observe. So I have pi of z dashed given theta. And then my design, I'm going to think of that as essentially it's going to be some censored or filtered version of z dashed that arises from the design d. So d of z dashed then is really the information that I'm going to get from the experiment if the full realization is z dashed and I use the design d. And then I'm going to have some utility function to quantify how useful this outcome d of z dashed actually is. And then the aim is to select d to maximize the expectation of u of dz dashed. So how does this work in the Bayesian framework? Well, the idea is to essentially identify the optimal designs as the posterior mode of some distribution. And what the trick is to treat the design as an additional variable, so an additional random variable. And now what one does is to assign a joint distribution to theta, z dashed, and d, where this joint density has the following form. It's proportional to pi of theta, pi of z dashed given theta, and u of d z dashed. Now, if we integrated this with respect to z dashed, then we would get pi of d given theta. Sorry, I'm using phi here for this density. Phi of d given theta. That would be proportional to the expectation of u of d given theta. In other words, the conditional expectation of u of d given theta. And then if I integrate with respect to theta, I get phi of d being proportional to the expectation of u of d. So in other words, my marginal distribution or marginal density on the design is proportional to the expectation of u of d. So if I can identify the mode of this marginal density, then that tells me what the most efficient design would actually be. So that's the idea, and because I only have to specify this density up to an unknown constant, then I'm able to use all the standard methods for constructing Markov chains in order to investigate this distribution. Okay, so there's quite a lot of problems that one might actually encounter in trying to do this. The first thing is to think, well, what would just a sensible choice of utility function actually be here? It would be natural for a Bayesian to base a utility function on, if you like, the whole posterior density that they get, as opposed to perhaps something to do with the shape around the mode. So one example that we could use, and I think Andrew was mentioning this kind of thing in his talk yesterday, would be to look at the Kullback-Leibler divergence between the prior and the posterior, which in some ways we could think of as being the amount of information or the extent to which we've changed our beliefs based on the experiment. Now, there's reasons why that may not necessarily be the most sensible thing to do. It would be sensible if somehow our posterior is typically going to be a more concentrated version of our prior, but it would be proportional to, it would be possible, if you like, to have a high Kullback-Leibler divergence by having a posterior which was somehow more diffuse than the prior. And I think Henry may make some comments on that in his talk on Friday. However, the framework that we're working in is quite general, so it's possible to slot in alternative formulations for a utility. But the main problem would be is if I actually try to use something which is based on the posterior density, then that posterior density itself is a difficult thing to get hold of. It's hard enough to investigate that posterior density when one just has a single epidemic that you want to analyze. If I'm now going to use some utility which is based on some integral which involves that posterior density, then I'm going to have to come up with some approximation to investigating that posterior density, which is what I'm going to talk about now. So how can we go about trying to, if you like, approximate the utility, if you like, using more efficient ways of getting at the posterior density? I'm going to consider, for the moment, a simpler model in which we don't have a latent period. So now I'm going to consider a model where I've only got 3 parameters, B1, B2, and R, so the primary, secondary, and the quenching term. Now, one of the reasons that it becomes vital that you find a way of approximating the posterior density is that if you're going to be designing efficient experiments, then they're probably going to have only a small number of sampling times. So compared with the experiments that we've seen previously, that probably means there's going to be an awful lot more in the way of unobserved infections. Okay, there's going to be typically far more infections occurring between my sampling times. So the basic problem of investigating that using MCMC becomes much harder. So let's suppose I've got an experiment where I only have 3 sampling times, T1, T2, T3. So my data would be I of T1, I of T2, I of T3. So I would get the number of infections at these times, but I don't know what's happened in between them. How can we approximate this this utility by first of all approximating the posterior density? Okay, well, we use a couple of approximations. First of all, kind of in the spirit of particle filtering, rather than work with a continuous prior, what we do first of all is to take a large sample of points from that prior and really work with a discrete parameter space, which is a sample from the prior. But the second approximation that I'll focus on is how we can approximate our likelihood L of theta using an approach which is known as moment closure, which you could think of as being quite closely related in spirit to the idea of diffusion approximations, but perhaps a slightly more general idea. So the idea is that we have our likelihood, and given that now I'm working with the model which is Markovian, I can actually write down what the likelihood is in terms of a product of conditional probabilities. So in other words, the probability I of T1 is equal to Y1 given theta, multiplied by I of T2 equal to Y2 given I of T1, and so forth. And then we approximate each term using moment closure. Now, actually, analytically, you can write down a solution to this, but it involves generalized Erlang distributions, and when one has a very large number of infections in between times, these are very nasty things to work with. So the numerics of actually trying to compute this exactly are actually very demanding, so that the moment closure in a way gives a quick way of trying to do that calculation, and I think in a way which is much more efficient. And the idea in the moment closure is that one essentially sets up a system of ordinary differential equations for the evolution of the moments of the system. Now, what I'm going to do is let j of t equal to I of t minus I of ti. So in other words, I'm looking at the number of new infections which occur after time ti. And then I set up, but just by looking at the expected increments to j of t, I'm able to formulate differential equations for the way in which the expectation of j of t, given I of ti, and also the expectation of j squared of t, so in other words, the second moment, given I of ti, for the way in which these evolve over time. Now the problem with this system is that when I look at the differential equation for jt, because this is a nonlinear model, I'm getting the expectation of j squared coming in here, so I'm getting the second moment in there. When I look at the equation for j squared, I'm getting the expectation of j cubed coming in. And if I keep on doing that, every time I put in a new equation into the system, it's not closed because a higher order moment actually pops up. So how could I get around that problem? Well, one way you can attempt to close the system is to say, well, let's assume a particular distributional form for j of t given I of ti, and impose that. Now, if we impose that distributional form, that will, if we do it in the right way, it will impose some relationship between the third moment and the first two moments. We're able to express the third moment as a function of the first two moments and close the system of equations. And the assumption, or the form which we choose for this, is to assume that j of t given I of ti is a beta binomial distribution, where I'll explain, if you haven't come across the beta binomial, I'll just say very briefly what it is. It's a beta binomial distribution with three parameters, and where the parameters alpha and beta are determined by the first two moments. Now, the beta binomial distribution is what you get if you first of all sample p from a beta, alpha, beta, and then you take an observation x from a binomial np. So in other words, think of it as being a binomial distribution where we allow p to be a random draw from a beta distribution. So there's a kind of analogy between the beta binomial distribution and the negative binomial distribution. If you take lambda from a gamma distribution and then take a Poisson lambda, you get a negative binomial. So this is a kind of analogous kind of process. So think of it as being an over-dispersed version of a beta distribution. And if we make those parameters scale so that they become very, very large, then we recover the binomial distribution. So it's a generalization of the binomial. If we impose that condition, then what we find is that, okay, we can write down expectation of j of the third moment in terms of the first two, and therefore we can get a system of two ODEs which we can solve relatively easily. Of course, one shouldn't use an approximation like this without at least checking it's appropriate for the model that you're looking at. And this is from a paper by a student, Isri Krishna Raja, where she tested out some of these approximations. Just very briefly, what this shows, what we've done here is to take parameter estimates for the system for the no trichoderma case and the trichoderma case. And what we do is look at the moment closure approximation. We start with no infection at time t equals 0. We then, if you like, iterate forward using the moment closure approximation and look to see what the beta binomial distribution looks like at 3 different time points, and then compare that with an exact simulation of the process. And we find that the beta binomial distribution, which is the dashed line here, the exact distribution is the histogram, and it tracks it reasonably well. In the case where trichoderma is added, you can see that the beta binomial distribution will actually underestimate, if you like, the probability of getting essentially no infection. But by and large, it does seem to be a reasonable estimate that we can use. So plugging that in then, it gives a very quick way of estimating the likelihood. Here's my 3 observation points with the numbers of infections. So how do I estimate the likelihood? Well, first of all, I iterate my system of ODEs forward. That gives me a beta binomial distribution, and then I pull out the probability for the particular observation I get. I then condition on I of t1, iterate forward, I get another distribution, and I pull out the probability. So I build it up in that way. So it's reduced the MCMC to, if you like, a numerical solution of 2 ODEs, which is much quicker in comparison. Okay, so time is getting on, so I'll move a little bit more quickly. So now at least we've got a very quick way of trying to get hold of u of dz. It's not going to be perhaps as precise as the full MCMC, but it renders then the experimental design algorithm at least tractable. So remember now that the aim is to draw from this joint density, which is proportional to pi of theta, pi of z dash given theta, and the utility of d of z dashed. Again, what we're going to, we use the kind of trick of assuming that our prior distribution on theta again, we'll draw a sample from a prior rather than work with a continuous prior. And again, Z dash represents the complete process. A very quick outline of the steps then for the Markov chain to investigate this state vector. First of all, we propose a new theta dashed and Z dashed, and then we're not really simulating Z dashed unconditionally from its predictive distribution, because now because we're looking at this joint density, which involves the utility of d of I. So we accept this pair with probability given by this minimum here. This is a standard Metropolis-Hastings step. We then also have to have a way of proposing changes to our sampling times. So the second stage of updating the design involves perturbing the actual sampling times which we use, and then accepting with a probability which is related to the change in the utility that I get for my new design compared with my existing design. Now note that because we're always doing this conditional on a full realization, I can change a time and I know what data I would get if I change the sampling time, because I have a complete set of infection times specified by Z. Okay, a couple of points to note here. Here we're just looking at designing a single replicate experiment. But if one was to repeat this, where we use multi-replicate experiments, but all sampled at the same time, then we would come up with broadly similar designs. A trick that one can use to make it more efficient is to sharpen the utility by, instead of drawing a single theta Z combination, we actually propose k-independent theta Z combinations. That effectively has the effect of making the marginal distribution for the design proportional to the kth power of the expected utility, so it sharpens it. But one obviously has to do a lot more computation if one's going to be drawing k-independent combinations. So what happens if we try to design experiments for this system here? I'm going to focus on the case without trichoderma, and this is reported in a paper a little while ago now, actually, in Biometrics. And just to remind you, this is what the 5 replicates look like. So what we're going to do is to look at first of all, the posterior densities for this data set for the 3 parameters B1, B2, and R. So that's the dotted curves in this diagram here. And we're going to use that posterior density to define our prior for designing the future experiments. So we first of all take a sample from that joint prior, the joint posterior, to give us our new prior pi dashed. Now at this point it's useful to kind of distinguish two scenarios that one might consider, because usually one thinks about designing an experiment to improve one's own understanding of the system. But depending on who that experiment is actually aimed at, who you're wanting to convince, there may be different approaches that you might take. For example, you might want to be designing an experiment to convince a skeptic, okay, or somebody who doesn't have the same belief about the system that you actually do. So we did find it useful to at least consider 2 scenarios here. The first one is what I would call the progressive design. So in other words, how should you repeat the experiment to maximize the expected information change with respect to pi dashed, where pi dashed is, if you like, your posterior from the previous experiment. So it's a bit like saying, well, I'm completely sure that my experiment was valid, and therefore pi dashed is a valid representation of belief about the system. Now I want to, if you like, learn more about the system, so I'm going to use pi dashed in order to look at the predictive distribution of the outcomes, but I'll also use pi dashed as the prior in my utility. The other approach you might think of as being confirmatory. Alex used the word pedagogic here. I've always preferred confirmatory. I thought it was a little bit pretentious, but I put it in case he's watching on the live streaming or something. So that's really saying, okay, how should you repeat the experiment to maximize the expected change with respect to pi? So it's a bit like saying, well, maybe there's something not quite right about the experiment, so I'm not quite going to adopt pi dashed, although I kind of think it's true. So therefore, I'll use pi dashed, if you like, to give me the predictive distribution of the outcomes, but I'll use pi as the prior in my utility. Depending on which of these you do get a slightly different outcome here. So some results from this analysis. Okay, first of all, I'll take a little bit of explanation here. The bottom right-hand corner is probably the key one to look at. What this actually gives you is the optimal observation times identified for experiments that have 1, 2, 3, or 4 observation times. In the case where, if we like, we use the progressive approach and where we also use the confirmatory approach. So look at the progressive approach first of all. The progressive approach suggests that if you're only going to use one observation time, then we use, I think that's 12 there. If you're going to use 2, then I think it's 9 and 13. Probably doesn't, yes, indeed it's there, 9 or 13. 3, we have these times, and then 4, we have these times there. What's interesting is it kind of says you're not going to get you're not going to get an awful lot of benefit from looking at the system early on. You're much better waiting for a while before you actually start to look at it. For the case of the progressive times, it's suggesting, again, you should be looking at it later on, but it's suggesting you should even wait later before you do that. I did trying to think qualitatively of how one might actually explain why you could get this difference. One of the issues is that if you look at that posterior distribution pi dashed, which is what we got from the first experiment, then there's a kind of confounding between the quenching of the epidemic and the secondary infection process. And if you want to move forward in your understanding from that, then you might want to try and resolve that confounding, in which case you might want to spend more time looking at the later stages of the epidemic where that becomes more important. But I say that's just a very sort of heuristic approach as to why this could be plausible. But of course, the proof of the pudding's in the eating, and something that's important to do is to say, well, if we take any of these designs and actually apply them retrospectively to the epidemic that we observed, do they give us something which looks like a reasonable amount of information? So in these 3 panels here, we show the posterior densities that we would get for B1, B2, and sorry, I think I've missed it there, that's for R, the quenching term. We show those posterior densities by applying those designs retrospectively to the actual data set which we have, and we also show the full, the posterior density for the full set of 14 observation times. And what is, I think, quite interesting is that for the 3 and the 4 observation times, they're very, very similar to each other. The 2 observation times does not seem to do so well, but both 3 and 4 give you a posterior density which is not radically different from what you would get from the full observation. Certainly if one was computing 95% credible intervals from that, there would not be an enormous difference between that and the full. But these are really kind of, this was our first foray into experimental design for this system. So I would say there is some perhaps surprising conclusions that say perhaps one can get reasonable information without doing quite as much sampling as done before. Remember, it's quite a reduction from 14 down to 3 or 4 observation times. However, something really is important to stress here is that we're always conditioning on the model. And that's fine if one has complete faith in the model, but if one is also wanting to use the experiment and perhaps to carry out tests of the model, then information early on in the process might be very important for testing that model. Now, I think there is an interesting challenge for Bayesians here, because Bayesian model choice, which would be the hyper-Bayesian approach to this, where one would have all these different models in an extended model space, becomes very, very difficult to do for epidemic model. And therefore, a more appropriate approach to model testing is to use kind of posterior predictive checks. So one's building in classical checks into the Bayesian framework. So it's not quite clear how one would attempt to design experiments to give you, if you like, good sensitive classical checks of your model in tandem with getting, if you like, nice posteriors for your distribution. So I should stress that. We're now extending this, and this is really moving on to the current work which is ongoing, although we do have a draft of a paper where Alex has been working on this and looking at more general utility functions which kind of take account of the actual cost of the experiment. Here, all I was doing was conditioning on having a number of observations and maximizing utility as measured by that Kullback-Leibler divergence. However, I wasn't really taking account of the actual cost of carrying out a given number of observation times. So therefore, we're also looking at having the number of replicates as a design parameter. He's also looked at much more efficient approximations for calculating the likelihoods. And rather than using the Mueller approach, actually, for what he's currently doing, finding that actually a direct simulation approach where one just takes a whole lot of different designs and investigates the expected utility, at least as a first step, seems to be working reasonably well. Also working with larger experimental systems and imperfect diagnostic tests. So again, I was making the assumption that we had a perfectly sensitive test. If one has a test which only detects an infection with a given probability, then naturally the optimal design is going to change. How are we doing for time? A couple of minutes? Yeah, okay. So currently we're looking at populations which are larger than the 50, so 160 in the population. Again, that increases the problem associated with unobserved infection times because one has a lot more going on in the course of the epidemic, so therefore it does become important to have approximation techniques. Again, looking at the SI model with the quenching, and this time looking at the number of replicates as a design parameter. It does make sense for systems like this not to allow sampling times to vary continuously. I would say it's very sensible to look at a discrete set of possible sampling times and optimize within designs that are constrained to cover these particular sampling times. Things like information gain and the cost-benefit analysis, one does have to take into account how much it costs to carry out an experiment. In the work that we're doing at the moment, we're making a broad assumption that the cost of a given design is proportional to 0.25 times the number of observation times the number of replicates, so the total number of observation times plus an additional term for the number of replicates. It's kind of like saying that the cost of setting up a replicate is equivalent to carrying out 4 observations. Again, instead of looking at Kullback-Leibler, we can look at much more easily computable measures of difference between a prior and a posterior. In this case, the difference in the log of the determinant of the covariance matrix, and alternative approximations to the likelihood. Rather than using the moment closure, which requires one to solve a system of ODEs, one can base an approximation to the likelihood by approximating these generalized Erlang distributions with gamma distributions of the same mean and variance. So throwing quite a lot of approximation in there, but the aim is to come up with some possible guidance that could be useful to people designing experiments. I'll just jump to the last slide here. These are, again, preliminary results for designing experiments for the Rhizoctonia system, but in terms of trying to come up with guidance that tells you, okay, if you have a total amount of cost that you can afford to deploy, what would the most efficient experiment to deploy be? Just to show, these are color-coded. What we find is that for costs up to 4, the most efficient experiments would just be a single replicate, and then these are the observation times for any given replicate. If you've got more than 4, then it becomes more efficient to do 2 replicates sampled 4 times each, and so forth. So for a given cost, one can identify what the most efficient design may actually be, with all the caveats that this kind of approximate analysis actually does. Now, of course, this will be very sensitive to the balance of cost between setting up the replicates and the number of sampling times. This curve here, for any given cost, captures essentially the expected information gain, so it tells you how much, in some way, that the information that you would get from that particular design would actually be. Again, something we're not doing is attempting to look at the balance between financial cost and information gain. How does one put an actual financial quantity or a value on information, which I think is a challenging thing to do, although there are methods for approaching that out there in the literature. So to sum up, I think we've probably got to the stage where at least qualitatively there is some useful guidance that can be given to people to help them set up these experiments and do them in the most efficient way. But I think there's a lot to be done. I think Bayesian methods do have a role here, but I think one has to constrain the models to be relatively simple in order to do that, and the number of replicates to be low. There's clearly the scope for using this sort of thing sequentially, where one uses the data gathered at a certain time to update the design of the experiment. When one moves to spatio-temporal systems, where now not only is it sampling times, but location of hosts, I think things do become much more complex, the kind of thing that Andrew was talking about yesterday. And a final point here is that everything I've said has been to do with design criteria, where one's somehow wanting to maximize the information on parameters. I think with epidemics, it's probably important to remember that the reason that the data is gathered is not necessarily to understand the parameters themselves, but in order to predict the future evolution of the epidemic and actually control that. So it may be more appropriate in the case of a real epidemic to be thinking of, if you like, utility functions which are based more on your ability to predict future events rather than your ability to understand the distribution of the parameters in that model. They're kind of blandly, you know, if you want to get a lot of information on an epidemic, a good thing to do is to actually let it run and observe it. But if you're trying to control it, then that's not the right kind of strategy. So your cost function really has to reflect what the whole purposes of the experiment is in the first place. And just a few references. Here's the paper that we're currently working on, some of the earlier work and some of the relevant Bayesian material. Okay, I should stop there. Okay.
Can I first of all make sure I understand, with the pedagogic design, what you're proposing is to use basically an informative prior for the design, but a vague prior, assuming you're going to be using a vague prior for the analysis, is that right?
That's right, yeah.
So does that not then mean you've got to do a lot more sampling? Does it sort of get out of control?
Well, okay, it's using, you're going to, if you like, use the prior that you used before you collected the data and essentially repeat the experiment that you did and do the same analysis from the Bayesian point of view. So it doesn't require you to collect, well, you're no more vague than you were at the start of the process. I mean, I was trying to think of an example where you would actually want to do this, and it may sound slightly frivolous, but suppose you submitted a paper where you'd done an analysis that you were very happy with and you got pi dashed as your posterior. Suppose two referees are happy, but referee number 3 says, I'm not very happy with your experiment and I want you to go away and do that again. Then they would expect you in your analysis to use pi as the prior. If you use pi dashed in some way, you're not addressing their concerns. However, if you are perfectly happy with your pi dash, then you may wish to use pi dashed in terms of predicting the outcomes and use a utility that looks at the difference between pi and the posterior that you get. So, I mean, it's that situation where that's why I called it confirmatory. It's a bit like saying, well, okay, suppose there was something wrong with the experiment. If I was going to do it again and carry out the same analysis from the Bayesian point of view in terms of what my starting belief was, that's what you would do. So I suppose the amount of, in terms of predicting the future outcomes, you're still using the same pi dashed, so you still have a sharper posterior than you did at the outset of the process. I probably wouldn't make too much of that. It just seemed to me that the issue of who the experiment is designed for is something that could be incorporated in the utility function. So if you want an experiment to design a skeptic, then use a utility function that reflects what their initial belief might be, not what yours would be. So Alex used pedagogic because he said if you wanted to teach somebody you didn't have your knowledge how to do the experiment, how would you do it?
relying on, if I understand correctly, relying on data to tell you what's going on. So, are you thinking that, for example, in a process where you have a pilot experiment, give the information, and then this is informative for further experimentation in future?
Correct, yeah. In fact, I kind of skipped over that when I was talking about the ongoing work, because that's exactly what Alex does, is to take a pilot experiment, which is maybe quite intensively sampled, right? A single pilot experiment, and use that to get a prior, and then based on that prior, sort of predict how you would do it, perhaps with fewer sampling times.
So if we think about, say, an outbreak in the outer space, and then we might not have the possibility of having a pilot run, we have to control it once it happens. So that would not be.
Yes, I would say that if you had an emerging epidemic where you know very little about what's happening, then I think it would be risky to make a lot of assumptions about a model and a prior and base your sampling strategy on that, rather like in some of the talks we saw yesterday. Until you kind of know what's happening there, one can't be too specific. So I think in the case of an emerging epidemic, it would be difficult to do that. However, if you take something like foot and mouth disease, after that had been running for a certain number of weeks, there was a lot of information was starting to be apparent about how far it would be likely to spread. So at that stage, it may be appropriate to do that. But you're absolutely right that if you had a very vague prior, then it becomes very, very difficult to do this. So I certainly wouldn't oversell it. That's a problem with the system, I would say, rather than the methods.
I have a not so serious question. I remember in the last outbreak of the bird flu epidemic, there was an outbreak near a research institute in Britain. Do you remember this? Is this experimental design or not?
Or you may be talking about the foot and mouth. There was not a foot and mouth outbreak close to.
I think it was a bird flu. I'm not sure. And there was an outbreak near such a research institute in Britain. I remember, and I thought, did they do experimental design at that moment? Did they really set it out to observe what happens, or was it just an accident?
I think you're talking about experimental protocol and health and safety issues there, but I'm not sure. I wouldn't like to comment on that.
Okay, if there are no further questions, then just thank you once again.